Okay, so today we're going to look at something called the mean value theorem. In calculus, the mean value theorem is actually a pretty important theorem, but it's generally used to prove other theorems. So it's not actually a theorem that we use to solve application type problems. So a lot of the examples we'll see are sort of more demonstrations of how the mean value theorem works rather than us solving some application type theorem. But anyway, here is a simple real world-ish example for the mean value theorem to get the idea of it. Imagine you drive from Peoria to Chicago. Let's say that is a distance of about 156 miles in 3 hours. How fast did you drive on average? So this is basically asking for an average rate of change, or average rate of change, or this is indeed an average speed here. And an average speed, this is pretty easy to compute. This is basically 156 miles in 3 hours. This comes out to 52 miles per hour. So we would have, if we did 156 miles in the 3 hours, we would have averaged 52 miles per hour. I'd like to point out here that this is really a slope calculation. That is, we did 156 is really ending position minus beginning position over ending time minus beginning time. So our average rate of change is actually a slope computation, right? This is an average slope, if you will. So the mean value theorem idea is the following, and that is, so if we know that we average 52 miles per hour over these 3 hours, what is something we can say for sure about the instantaneous velocity? That is, instantaneous velocity is like what you see when you glance down at your speedometer as you're driving. That's our current speed, or momentary speed, instantaneous speed. So what the mean value theorem says is that the instantaneous velocity at some point, at some moment, and again, this is actually, it has to be at least one moment, but it could be others as well. So the instantaneous velocity at some moment was also equal to 52 miles per hour. So this is a pretty logical idea. If we average 52 miles per hour on the whole trip, it means we must have been going faster than 52 miles per hour than on some of the trip, and slower than 52 miles per hour at other points in the trip. And now we cannot put our car in a time warp. The only way our car can be going from slower than 52 to faster than 52 is by, at some moment, at least one moment, becoming 52 miles per hour exactly. So this is the idea of the mean value theorem. It relates an instantaneous rate of change to an average rate of change in some interval. So try to generalize this idea is the following. So this is basically what we have said, right? Our instantaneous rate of change at some point in the inside of the interval has to be equal to the average rate of change over the whole interval, over the endpoints. So this is kind of like, graphically, this is kind of like our secant slope. Our secant slope has to be equal to the tangent slope at some point during this interval. So this is kind of the generic way of stating the idea of the mean value theorem. There are some conditions for this to be true. For example, we cannot have a function that is discontinuous. A discontinuous function can have a jump in it. And if you have a discontinuous function, it could jump over 52 miles per hour. So that is not allowed in the statement of the mean value theorem. We would require at least continuous, and we also require differentiability. So remember, if a curve has a jump in it, it might jump over 52 miles per hour. If a curve has a sharp corner in it, it can also, again, jump over a bunch of slopes, right? So this one has a certain negative slope, this one has a certain positive slope, and it jumps over the slopes in between as you go from left to right. So this is also not allowed. You cannot have something that is not differentiable. So again, functions with sharp corners are not differentiable at those sharp corners, but we will mention this here momentarily. So to get the idea of the mean value theorem, we're going to first start with something called Rolle's theorem. Rolle's theorem is actually just a specific case of the mean value theorem. It is actually an easier case than the full-blown mean value theorem, which we will move on to here shortly. So the Rolle's theorem is kind of like a mean value theorem light. It's an easier starting point. And in a more technical sense, the way the mean value theorem is proven in mathematics is you actually start with Rolle's theorem. Rolle's theorem is a simpler theorem and easier to prove. And then the Rolle's theorem is used to prove the full-blown mean value theorem. So the good news here is for you, we are not going to look at the proofs of these things, but you should understand these two situations, or these two theorems. So first off, Rolle's theorem. So for Rolle's theorem, you have three conditions. You have to have a function that is continuous on a closed interval from a to b, differentiable on the open interval from a to b, and it also has, in Rolle's theorem specifically, we have the necessity that the output at the beginning is equal to the output at the end. So graphically, it's like they're at the same height at the beginning and at the end. So if those things are true, then this is the conclusion. There is at least one number, call it C, in the interval from A to B, such that f prime of C equals 0. So I'm going to draw a picture of this situation, and this should become clearer. So imagine, here's our first example here, first picture example of Rolle's theorem. Here's the graph of A, graph of B. So I need to draw a function that is continuous and differentiable. So no jumps, gaps, or asymptotes or anything like that, and no sharp corners on this interval. And I have to start and end at the same height. So let's say here is f of A, here is f of B on the same height. So here's where f of A equals f of B. And let's suppose we have a graph that does something like this, a nice graph, no jumps, gaps, holes, sharp corners, or anything like that. Okay, then what the mean value, what Rolle's theorem states is that somewhere in this interval from A to B, there is a point where f prime of C equals 0. So there's somewhere a horizontal tangent. So the significance of this is why horizontal? It's because of the following. It's the idea that because f of A equals f of B, the average rate of change on this function as you go from A to B is in fact 0, right? Because it is the average rate of change would be the slope between this point and this point. If they are the same height, rise over run, the slope is 0, yes? This has a secant slope, if you will, equal to 0. So what is guaranteed by Rolle's theorem is somewhere on the interval, it looks like it's about here, somewhere on this interval, there is a place where we have a tangent slope also equal to 0. Again, the significance here is these slopes are parallel, yes? And again, the point is that this place right here must exist. This is what the mean value theorem, Rolle's theorem currently tells us. Rolle's theorem tells us this C exists between A and B. So this is the idea. And again, I think if you think about it, it's actually fairly obvious. The theorem is a little hard to read, but if you try and draw a picture of the situation, I think it becomes fairly obvious. I'm going to draw a second picture of our situation here just to illustrate something. Rolle's theorem's conclusion says there exists at least one such number. So there has to be at least one place. There can be multiple such places. So similar picture here, A to B. We have a place where f of A equals f of B. And I could have a graph. Maybe I have a graph that does something like this. Right, something like this. Again, what we have here is basically a secant slope from x equals A to x equals B that is equal to 0. And in this case, we might have multiple places where we have horizontal tangent lines. So we can have multiple places where this occurs, C1, C2, and C3, for example, just the way this one looks. There could be 3. So there has to be at least one, but there could be more than one. So what Rolle's theorem tells us is that such a C value exists. It does not tell us how many, it's just one or more, and it does not tell us what that C value is, just that it must exist. So this is Rolle's theorem. All right, so let us try an actual example here. So Rolle's theorem, let's use this function as a example, or as basically as a demonstration. So again, these questions are really more a demonstration that the theorem works rather than a solution to some sort of application or some sort of calculus problem. It is really just a demonstration of the theorem. So the question is to verify that this function f of x equals x times the square root of x plus 6 on the interval from -6 to 0, closed interval, satisfies the conditions. If it satisfies the conditions of Rolle's theorem, then the conclusion of Rolle's theorem must be true. That is, there would have to be a C number on the interval from -6 to 0 where we have a horizontal tangent. All right, so the conditions are 1, we need that f of x is continuous on the interval from -6 to 0. So is that true? Well, how do we do continuity for a non-piecewise function? And the answer is that f of x, a non-piecewise function, are continuous on their own domain. So this was the nice conclusion we came to a while back. I think it's section 2.5. Continuity, if you need to know the continuity of a non-piecewise function, the good news is it is simply the domain of the function. So the domain here is, well, my only domain issue here is x plus 6. X plus 6 under the square root must be positive or 0. It cannot be negative. This means that x has to be greater than or equal to -6. So this is where we are continuous. We are continuous on -6 and above. So hence we are indeed continuous on the interval from -6 to 0. So that condition is checked. That is true. Step 2, we need f of x is differentiable. Is f of x differentiable on -6 to 0? Is this case? Well, in order to judge differentiability, we want to see that the derivative is well-defined and continuous. So that is f prime well-defined and continuous? Continuous on -6 to 0. Is this the case? So let us see. We're obviously going to need to find f prime of x. So f prime of x is going to require a product rule. Is derivative of x times square root of x plus 6 the way that it is, plus x times derivative of the square root of x plus 6 is a 1/2 x plus 6 to the negative 1/2. This is written, can also be written, cleaned up a little bit. X plus 6, square root of x plus 6, plus there will be an x over 2 root x plus 6. So this is our function. So similar to the first condition, how do I know if we are differentiable? I need the first derivatives to be continuous on this interval. So we look at the domain here, the domain of f prime. Well, we need, again, I need x plus 6 to be greater than or equal to 0. But I also need from this other one, since I'm dividing by this one, I also need x plus 6 to be strictly greater than 0. So I can note to myself that, well, if x plus 6 is strictly greater than 0, then I don't need that condition. If x is strictly greater than 0, then this condition is met. So I really just need to consider this guy right here. X plus 6 needs to be greater than 0. This is x needs to be greater than -6. So yes, f prime of x is differentiable on -6 to 0, because it is differentiable on all values greater than -6. So yes, we are differentiable there. The third condition of Rolle's theorem is in this case, f of -6 equal to f of 0. Again, let's try it. F of -6 will be -6 times the square root of -6 plus 6. Well, that is -6 times 0 equals 0. On the other hand, f of 0 is 0 times the square root of 0 plus 6. That is also equal to 0. So the third condition is also satisfied. So the three conditions, the conditions of Rolle's theorem are satisfied. This means that the conclusion from Rolle's theorem must be true. So we can say, hence, there exists at least one C such that f prime of C equals 0. So this is the conclusion. Lastly, then, we're being asked to find this number C. The theorem doesn't tell us, but I simply need to solve that equation. F prime of C is the square root of C plus 6 plus C over 2 square root of C plus 6. We set this equal to 0 and solve. So this would be C over 2 times the square root of C plus 6 is negative square root of C plus 6. Cross multiply, and we get that C equals -2 times C plus 6. So C is -2C minus 12. So 3C equals -12, and C must be -4. C must be -4. So the significance of this result, the significance of this result is to note that C equals -4 is on the interval from -6 to 0 as predicted by Rolle's theorem. Right? This is the significance of this result. We had to have a solution to this equation in that interval. That is what Rolle's theorem is telling us. All right, so that is the idea of Rolle's theorem. Okay, next up, let's take a look at the full-blown mean value theorem. Again, mean value theorem is a generalization of Rolle's theorem. It is similar to Rolle's theorem, but we drop the condition that f of a equals f of b. So the beginning, the function at the beginning does not have to end up at the same output as the function at the end. And I think, again, a picture is worth 1,000 words here. This is, again, fairly easy to understand if you think about the proper picture here. But this is the statement of the theorem. We still require that we have a continuous function on a, b, closed interval from a to b, a differentiable function on the open interval from a to b. And then if that's the case, there exists at least one point, x equals c, inside the interval from a to b, where this must be true. And again, notice what this says. This says tangent slope equals secant slope. This is secant slope from the beginning to the end of the interval must be equal to the tangent slope somewhere in the middle. So again, a picture worth 1,000 words here. Let's draw a couple possibilities. Here, let's say here is our interval from a to b. And let's suppose we have a function now. It starts here. Let's say it ends over here. So I can have a graph of a function that does something like this, perhaps fairly simple function. And again, it has to be nice, continuous, differentiable, no jumps, gaps, asymptotes, no sharp corners. Yep. So this time we are looking at the secant slope from one end to the other, which would be the slope of this line segment joining the ends together like this. And what the theorem guarantees is that somewhere on this graph, and I'm going to eyeball it as being around about here somewhere, we have a tangent line. That's not very good. We have a tangent line. Still missed a little bit, but we have a tangent line here somewhere. And again, what we're looking for is the tangent line has to become parallel to the secant line somewhere inside this interval. So in the graph I've drawn here, the first picture I've drawn here, there is only one such place, yes. But somewhere on this interval, this would have to become a parallel tangent line to this secant line. Again, a slightly more generalized picture is that this can happen in more than one place. So we can start here and here. We could have a graph that does something like this. And the same theorem would still apply. This would be our secant slope or our average rate of change. And it would have to be, again, there would have to be places such as roughly here, it looks like, and roughly in here somewhere, it looks like. We must have places where our tangent slope becomes equal to the secant slope. So this second picture, there are two such places where this could happen. So again, the theorem, the mean value theorem, doesn't tell you how many places it happens at. It just guarantees that there's at least one, and it does not tell you where this happens, just somewhere inside the interval. It doesn't tell you what that is. So this is our situation. And again, Rolle's theorem is simply what you get if you move this second output at B down to be on the same horizontal line at A. Rolle's theorem is that version of the mean value theorem. All right, so let's work on a demonstration of the mean value theorem. Again, we are not going to look at the proof of these theorems. They are a little tricky. It is in the textbook if you care to look, but we will not be worrying about those proofs. So let's look at instead a demonstration of the mean value theorem. So how would this work? So the question is, show that this function satisfies the hypotheses of the mean value theorem on the interval from -2 to 2, the closed interval from -2 to 2. And then we're going to find, so if this function satisfies the hypotheses of the mean value theorem, the conditions, if you will, of the mean value theorem, then the conclusion of the mean value theorem must be true. And that is the C number exists somewhere where f prime of c is equal to the secant slope. So let's look at the conditions. think you'll find the conditions here are actually pretty easy to check with the hypotheses. Number one, is f of x continuous on -2 to 2? Is this true here? So I would argue that f of x is a polynomial all polynomials are continuous for all real numbers. So f of x is certainly continuous from -2 to 2. So that checks out rather easily. Condition number 2, is f of x differentiable on the open interval from -2 to 2? So similarly here, well, I guess I should be looking at f prime. So f prime of x is going to be 3x squared minus 2. This is also, again, a polynomial, therefore continuous everywhere. Hence, this implies that f prime is certainly differentiable on the interval from -2 to 2. So this is well defined. It is continuous. So this means the derivative exists. So yes, this function, the conditions of the mean value theorem are satisfied. So this means that there must exist a value x equals c such that, well, let's put it this way, such that -2 is less than c is less than 2, and f prime of c is equal to, in this case, it would be f of 2 minus f of -2 over 2 minus -2. So let's evaluate that here. Plenty of room here. So this is going to be equal to what? So f of 2, this is 2 cubed minus 2 times 2 plus 5 minus, this one is -2 cubed minus 2 times -2 plus 5 all over -2 minus double negative is plus, this is a 4. So this secant slope is going to be 8 minus 4 is 4, 4 plus 5 is 9. This is -8, positive 4, so -4 plus 5 is +1 all over 4. This is 8 over 4 equals 2. So this is our secant slope. So to find c, we solve f prime of c, which would be 3 times c squared minus 2 equals 2. So here's my first derivative. This is my secant slope. Set them equal to each other, solve for c. So this is 3c squared equals 4. This implies c squared is 4/3, and hence c is plus or minus the square root of 4/3, or plus or minus 2 over √3. So these would be our possibilities here. So we do have 2 c values here. I don't know, I have to check whether they are in the interval or not, but at least one of them has to be, yes. Again, to check if they're in the interval, it's probably helpful to turn them into decimal numbers. I get these to be plus or minus, in fact, 1.1547, 1.1547. And you will notice then that, as predicted by the mean value theorem, both C values are in the interval of -2 to +2. One is -1.15 or so, the other one is +1.15 or so. And again, this is what was guaranteed to us, that there would be at least one by the mean value theorem. Okay, so what remains here is just a couple of, I don't know, applications, an attempt to have an application example. I think this next question is fairly obvious, but I think there's a little arithmetic to do, but ultimately it is an example of the mean value theorem. So note here, to get on a toll road, which has a 65-mile-per-hour speed limit, a driver has to stop and take a ticket that lists the entrance point. The ticket also has a timestamp. So then when going to pay the toll, when he or she exits 50 miles later and 45 minutes later, the driver is surprised to receive a speeding ticket along with the toll. Is there sound evidence that the driver was speeding at some point on the toll road? So we know that the driver goes 50 miles in 45 minutes. So we can quite happily compute an average speed, yes, an average speed. The average speed here would be, again, notice that 45 minutes is actually 0.75 hours. So since our speed limit is in miles per hour, we need our average speed in miles per hour. So average speed would be 50 divided by 0.75. And again, that is actually could be thought of as a slope calculation. It's 50 miles at the end, 0 miles at the starting point, 0.75 hours at the end, 0 hours at the beginning. So we don't need this, but again, this is a slope computation. If you do this math, you get 66.67 or so miles per hour. So this was this person's average speed. I think then it's fairly obvious if they average 66.67 miles per hour, then they must have been speeding. They must have been doing more than 65 miles per hour somewhere. They must have been doing 66.67 miles per hour at least one moment during this drive. I guess, and again, I do like that idea in that it's, I think, a pretty obvious idea, but realize that it is just the mean value theorem. So note that it is the mean value theorem in math that guarantees that the driver must have, the driver must have been doing 66.67 miles per hour at least one moment during the drive. Again, this is actual proof, right, that he was speeding, he or she. You might think it's a little harsh to get a speeding ticket for being 1.67 miles per hour over the speed limit, but they were in fact speeding. Again, I'm being a bit facetious, but we know they were at 66.7. We would know that they were faster than that too, right? There's no way that they can drive at exactly 66.67 because they started from a standstill. So they were going faster than 66.67 at some point. And again, this is not a difficult question. It's a fairly obvious question, but it actually is a logical and natural conclusion due to the mean value theorem. All right, here's another little example. Again, this is similar to the demonstration ones we were doing, but just sort of you'll see some questions maybe asked in a slightly different way, set up in a different way. So let's give that a go. Consider the function f of x equals 4e to the x over 7 on the interval from 0 to 7. So first part is find the average slope over the interval from 0 to 7. So average slope. Note that this is really the same thing as average rate of change. Average rate of change will be, again, it's a slope calculation, rise over run. It is f of 7 minus f of 0, f of 7 minus f of 0 over 7 minus 0. So what is that here? This is f of 7 is 4e to the 7 over 7 minus 4e to the 0 over 7 all over 7. This is 4e to the 1 minus 4e to the 0. E to the 0 is 1. And so this is what we get. So this is our exact average rate of change. For our purposes, we can, again, we're being told to turn it into a decimal. So this is 0.9, I get this to be 0.9819. This is our average rate of change. Second part of the question is, why does the mean value theorem apply to this function? So this is really a matter of the conditions, yes? Does it fit the conditions of the mean value theorem? So number one, is it continuous on the interval from 0 to 7? So this is essentially, again, the domain of 4e x over 7. The domain here is all real numbers. So this is indeed going to be continuous. It is in fact continuous for all real numbers, so it is continuous on this interval. It is continuous on the interval from, I forgot what it was, 0 to 7. It's continuous on the closed interval. On the closed interval from 0 to 7. This must be true. Similarly, we need to think about, is it differentiable on the open interval from 0 to 7? So these are questions. Well, we would need to look at the first derivative, f prime of x. This is a little chain rule here, yes? The function is 4e to the x over 7. So the derivative, the 4 would sit out in front. We do the derivative of the outside function, which is e to the power of, leave the inside the way that it is, and then multiply by derivative of the inside is 1 over 7. So this is 4/7 e to the x over 7. And again, fairly quick and easy. We can note that this is also continuous everywhere. So the derivative is well defined and continuous. So we have something that is differentiable on the interval in question, which is from 0 to 7. So this is, again, also true. So the mean value theorem does apply to this function because we have the two conditions met. So what can we conclude about f of x? So the mean value theorem tells us there exists at least one c value such that, I should say, at least one c value on the interval from 0 to 7 such that this is true. We must have that f prime of whatever that c value is equal to f of 7 minus f of 0 over 7 minus 0, which we happen to have computed up above. This is 0.9819. So this is what must be true. So what is this c number? Well, we find it just by solving that equation. We need to solve f prime of c equals 0.9819. This is, so we just found f prime up here. This is 4/7 e to the c over 7. That's f prime of c equals 0.9819. So just using this decimal number for 4 places. So e to the c over 7 will be 7/4 times 0.9819. I think you'll find I evaluated that to be 1.7183. So let's go up here. So we can then take ln on both sides. Ln of e to the c over 7 would be ln of 1.7183. Again, ln, e undo each other. These are inverses. So this is c over 7 equals ln of 1.7183. So finally, c is 7 times ln 1.7183. So I can evaluate this on my calculator. I get this to be 3.7893. So this is the C number sought after. A couple of things to note is there appears to be only one C number here. If there was another C number, we would have had to have another solution to this equation. We do not. So there is only one C number. Hence, if we did it right, this C number had to be in the proper interval guaranteed by the mean value theorem. So note, C is in the interval from 0 to 7. Right, this is what was guaranteed, that it existed and it would be between 0 and 7. So that is what we have in this case. All right, so that is the mean value theorem. Thank you, and that's the end of the video.